Professor Jaya Prakash Champati, and we'll be speaking on getting the best of both worlds, IoT and Edge, using hierarchical inference. Professor Champati is an assistant professor at IMDEA Networks Institute, where he leads the Edge Networks group. His general research interest is in the scheduling of communication and computation for emerging applications in edge computing systems, IoT, cyber-physical systems. Prior to joining IMDEA, he was a postdoctoral researcher in the Division of Information Science and Engineering, EECS, KTH Royal Institute of Technology, Sweden. He obtained his PhD in Electrical and Computer Engineering from the University of Toronto, Canada in 2017 and his MTech degree from IIT Bombay, India in 2010. Prior to joining PhD, he worked at Broadcom Communications, where he contributed to the LTE MAC layer development. He was awarded the prestigious MSc postdoctoral fellowship in 2000 at IEEE National Conference on Communications India 2011. Before I move on to the talk, we request the online audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, you may unmute yourself and ask Professor Champati directly or type them in the chat box. We'll relay your question. And for the in-person audience, we have arranged for high tea at the coffee hut. Please help yourself to continue the conversation over coffee after the talk. Over to you, Professor.
Can you write here? Yes, thanks a lot, Anita, for that introduction. And thanks a lot for inviting TN and TNS. Thanks a lot for that. It's good to be back. The last time I was here, I was here for NCC conference, National Conference on Communication, back in 2007. Definitely, I got a best award at that time. So it was a good memory. I start with the talk today. The talk is titled "Getting the Best of Both Worlds Using Hierarchical Inference." So yeah, before going to the talk, a short detour, just letting you know what IMDEA Network is. It's a small institute that was started back in 2007 when Europe was trying to accelerate the research efforts, and they started all the European funding projects, and they set up as part of that some institute in Spain, similar to IMDEA in France. So these institutes work with close by universities. So specifically, IMDEA Network works with University Carlos III. So the university confers the PhD degrees, and we hire PhD students. We open position for PhD students and supervise. We work more like a US department. So we are all faculty level postdoc and 40 PhDs. In total, will be around 80 people at the institute. The institute research is focused on data networks in general. So network systems and algorithms, wireless networking, network measurement and analytics, security, distributed computing. I myself am leading Edge Networks group. I have 2 PhD students and a postdoc. So please, anyone, if you visit, if you want, because I am not posting there for posting. Which one is good? Oh yeah, that's a good question. Maybe I should ask you, right? Shortly. Yeah. So the outline of the talk is this. So I just briefly introduce edge computing, which you already know, and then quickly talk about edge intelligence, and then they introduce the main concept I want to drive to today's talk, that is hierarchical inference. So once I define what hierarchical inference, I wanted to convince you that hierarchical inference, which is ideal, in the ideal case, you cannot implement hierarchical inference, but I'll show 2 application scenarios where we can do it along with the benefits of hierarchical inference. But for the major part of the talk, I will focus on image classification because implementing hierarchical way, the image classification is the toughest one, and we'll spend more time in this talk for that. So yeah, going back almost 20 years ago, People started building data centers, okay, to cope up with the big data revolution. So all these users or enterprises are generating so much data, and all this data is being processed in this data center. And until 2008, 2009, people realized that more and more smartphones are out there, and more sensors are out there, and they are generating even more data. Okay, and then bringing all that data to the data center is a problem. Why? Because you have latency, okay, that gets added up first for moving data from the devices to first contact point, like a cell tower, and then from there to the internet. Okay, these two factors add a major delay. And the second question is it feasible to move all this data? So for example, autonomous cars generate GBs of data in a matter of seconds. Okay, so bandwidth constraints kick in, and it might not be even feasible in most cases unless you have private. And then there are more important aspects, data privacy and security aspects, which people are concerned. Okay, so to alleviate these aspects to some extent, we move back to a distributed computing setup where you want to move some computing part to close to the points where the data is generated. Okay, any computing infrastructure that is in between the end devices and the cloud, you can call it as edge. Okay. How can this alleviate? We are trying to minimize the delay by making it physical proximity. Here I am showing edge server is deployed and by the telecom provider. Okay. And then the bandwidth is still an issue, but at least you don't have to clog the core network. Okay. Okay, well and good. Now after 10 years, I mean almost like 2003, 5 range, 2012. Okay, these things were going on, and then suddenly there was AlexNet and then image classification, which has been which has received a lot of attention for the past 20 years. Actually, received more attention after that because of the all these networks were performing 10 to 20% better than all classical techniques that were used before. And then people started using machine learning algorithms. They are training in big data centers. And we are back to the same question again. Can we move all these images that you create at the end devices to data centers and then process it? And we have similar answer. Okay, you just try to get this machine learning algorithm work at the edge, right? So with that, then this term edge intelligence has gone out of it. Okay, it's essentially you're trying to deploy machine learning algorithms on the edge server, and now on top of that, onto the end devices also. So there is so much work going on to reduce the machine learning model size, DNN model size, and fit on small memory resource constrained devices as well. So in this, I mean, so the edge intelligence is something where you want to make all these things work. Okay, get data, do inference, I mean, make and devices smarter. So in this realm, what I focus mainly is this resource constrained IoT sensor, and what I focus is on ML inference, not training. So essentially this is the schematic. So I have an access point and an edge server, which has edge server can host a big DNN model, and then there are IoT sensors. They may also have small DNN models. Okay, and then in this case, all these models are already trained. Okay, they are just being now used in the inference cycle of the machine learning like that. Okay. So let me switch gears and coming to the problem. So I want to discuss about what are the benefits of remote inference, or what are the benefits of local inference. Let's talk first about the remote inference. So if all these IoT sensors are collecting data and then sending this data to an edge server, first, I mean the same aspects we have gone through, okay, before will kick in. Okay, when we are sending data to remote, something remote is always a delay adding element, right? And because IoT sensors there, I mean, there are so many number predictions there, but there are at least billions of them, even more than the population today, right? And if you are looking at even small networks where you have thousands of IoT sensors, okay, even in that case, bandwidth will still be a constraint. Okay, we'll also look at that part later. And then the third constraint, and that is not that clear from the start, is the energy efficiency of the system when you are moving data from one place to the other and doing it well. The reason is the DNN models are huge, they are run on big servers, which are energy hungry. Okay, even if you are doing some say 1,000 instances within a few minutes, that itself will have more effect than doing inference on 1,000 different IoT sensors, because these sensors will consume energy in milliwatts. Okay, whereas these servers consume energy in terms of watts. Okay, of the power. So so then the question is, can I just embed small DNN model from IoT sensors and do the instance and are we done? I mean, if we do locally, then all those three will be taken care of, right? On those three issues. Is there any catch? Any guess?
Accuracy.
Right, accuracy, right? So because not all decisions given by small size DNN, which are actually they are compressed with the trade-off of accuracy, right? So that's the catch, and the question then is, if once they have this less accuracy aspect, even though doing local inference is beneficial in all the aspects of requiring less bandwidth, no bandwidth if you don't want to transmit anything. We need first such kind of algorithms which give high accuracy, but they cannot. Okay, that's the main issue. So to actually leverage the benefits of remote inference of higher accuracy and the benefit of doing local inference is where I'm proposing this hierarchical inference. I mean, this idea is like very natural. Let me just okay, let me just define the in a very simplistic manner and come to it later on how to implement this. Let me define simple data samples. So whatever data samples you are collecting, image, okay, image or any time series data. Let me call simple data samples when a local algorithm on an IoT sensor use correct inference on that data sample. Okay, and I call it a complex data sample if it gives a wrong inference on that data sample. Okay, now what HI does is asks the IoT sensors to accept local inference for simple data samples and offload complex data samples for remote inference. So this is the ideal scenario I want. Okay. I know that if for any simple algorithm I may not classify the entire decision space correctly. So I will take the correct classifications. Okay, talking about image classification there. Correct classification when the local algorithm is giving this correct classification. If it is giving wrong, I will offload. Okay, in that case, I can leverage the benefits of here.
So how do you know that this is a complex? How do you know it's wrong?
No, this is just the ideal definition.
Then I understood, but this is the question. Like, if you do the complexity, how to do it?
Right, exactly. So we will actually the entire talk is about me convincing you that it can be done. Maybe not in 100% efficient way, but to some extent we can actually do it. So and then the application here.
So are the observations across those nodes correlated? What are they? Different?
So right now, I am not talking about any specific application. Can you tell me an application here?
There are a bunch of sensors which are observing the same process.
Right. So in that case also we can think about delineating this space where you can do some decisions locally and where you can offload decisions that cannot be done locally.
In this model, it is a general model.
Yeah, this is the general setup. It is a general setup where I'm trying to classify, trying to somehow partition the set of data samples where local algorithm, we leverage the full strength of local algorithm before moving on to forwarding it to the remote one. Okay.
We have one question from our online audience. Okay. Please unmute yourself and ask.
Hello,
Yes.
hello, am I audible?
Yes. Yes.
Yes, so my question is how you differentiate the complex data and simple data. Actually, data you are collecting from edge sensors. So how you differentiate it for two types of data?
Yes. I will show two examples. Okay, this is not straightforward at all, and one can question how this can be done. But I'll show two example use cases, two example scenarios, and the whole point of this talk is to convince you that it can be done in at least some application. Yes. Okay. So I just want to give a quick note on related work since I'll be focusing on image classification for more part of this talk. So there is a lot of work on doing hierarchically this inference on images using DNN partitioning, where you divide the layers of deep neural network between an edge device and an edge server. Okay, and try to minimize the communication, the data that needs to be communicated. So there has been work for last 5 years, and then there is another approach called early exit. So these two are very focused on specific DNN features. Okay, in early exit, what they do is you have an IoT device and you have you can embed get embedded DNN, small size DNN on that, and try to infer, do an inference and try to exit it at some layer with lesser accuracy. Okay, depending on the trade-off between how far you go in into how far you process across the how far you go in the DNN, you get different accuracy. So these two are the approaches that were already being studied for some time. So what I perceive is we can have any algorithm on the IoT sensor or any algorithm on the edge server. And I ideally think them as independent algorithms. So you can use independent algorithms and still make hierarchical inference. So you don't have to, you don't have a dependency. So that even if you don't have a connection, you still have some kind of accuracy on the IoT sensor. So in that sense, hierarchical inference that I am looking at, we are trying to partition the data sample and we can run independent algorithms. This is the contrast with the existing work.
I think here's another question.
Yeah.
Yeah, please ask.
Just type it in case
Yeah, we have two more questions in the chat. Someone asked that simple data can be of any type, like image, video, audio, voice, etc.
Yeah. So the data can be image, audio, or time series, anything. So we want to differentiate within that data universe, whatever we have. We want to differentiate. This is what I'm just trying to show. There can be applications where you can differentiate a large amount of data without being forwarded to the remote for the remote inference using simple techniques. Using simple, you may also use digital signal processing. You may also use statistical techniques. Okay, and the rest only we need the big mind out there on the remote. Okay, so but if you have more questions on simple and complex data samples, I mean, it will get clear once we go forward in the talk.
Okay. Another question is that what is the smallest footprint of edge computing can be achieved with the present day technology?
The smallest footprint. footprint in terms of energy
That he
or
didn't-
memory or
Yeah, that he didn't mention. We'll wait for his
So,
next
yeah.
question. Yeah. So please continue.
so yeah, so I'm just trying to iterate the questions already asked. Is it really feasible? Okay. The first, I mean, there are so many things we need to take care, right? So first we need a local algorithm. Okay, for any application, you need an algorithm, local algorithm that can give inference or a decision to some extent that is correct. Okay, or to some so we need to design such kind of algorithms and then embed them on the IoT sensor. That algorithm shouldn't take more computational energy than transmitting this data sample, right? Otherwise, why do I care? I just transmit, right? Because for me, IoT sensors, battery is more important. Okay, and then yeah, as I said, it needs to provide correct inferences for large number of data samples. So then the catch-22 situation is how does the IoT sensor know whether the local algorithm made a correct inference, right? And especially in image classification, you'll see that it is not possible at all. As I said, it's not easy. No, there is no easy answer, and you cannot, in general, implement HI hierarchical in a hierarchical fashion. It is heavily application dependent. We'll see that, but I'll show two application scenarios where you can do it. So one is machine fault detection, and one is image classification. So I'll quickly jump to machine fault detection. This is a very straightforward case. Let me consider this data set from Case Western Reserve University. So this is this is most widely used data set for analyzing machine fault detection and evaluating performance of algorithms that were proposed for this. So this data set has, I mean, in a lab they collected the voltage values for the vibrations when they use these rotating machines, and what they collect is the voltage values for having a sensor on top of the machine. That's it. So what they want to detect is the fault in rolling element bearings. These rolling element bearings will be actually as I show in the yellow arrow. So at this end and at the other end as well. Okay. And usually faults happen typically in this REV. And the faults can happen either on the outer layer or inner layer or on the rolling element itself. That is okay. So in this data set, they introduce the damage sizes on each of these three layers. Okay, and so with 3 damage sizes and 3 layers, you have 9 faults. Okay, and once you have the data set, you want to differentiate normal working conditions and these 9 faults. Okay, so you have 10 states to differentiate. Clearly, I mean, this is a very well studied problem. It's there for decades, and already just digital signal processing techniques themselves can do a pretty good job till 95%. Okay, and then the latest one is the CNN. You might have this. It does 99.91 accuracy because it takes the data, it just creates images 64 by 54, and then does the image classification. Okay. Now my question is, can we achieve 99.91 accuracy, okay, without collecting this much amount of data? So here in the last point, they are collecting data at 48 kilohertz and sending to a server. Okay. Can we do with very less data, okay, and still achieve the same accuracy? Any idea? Okay, just okay, sorry. This slide is to just say how much. If I use 2 bytes and then I'm sampling at 48 kilohertz, so I need 78 kbps just for one rolling element bearing. Okay, and then on a factory floor there are so many of them, and each rotating machine has so many REVs. So you can easily think of MBs for 10 machines, right? So again, I'm repeating the question: can we reduce this number of samples and still achieve the same accuracy? So the hint is, so this is the question. The hint is typically the machine runs in the normal state, right? So if I can differentiate the normal state locally on the machine itself, I can only then focus on faulty states, right? So can you think of a simple approach here? Can you guess how to differentiate the normal working condition? Anything that working? Any difference? Yeah.
We transmit the faults which might be there, which are different from normal state.
Yeah, so that is the question we want to solve, right? So you are having this time series data, which are simple voltage values of the vibration, right? I mean, you guys agree that if the machine is in a faulty state, okay, you get high voltage values because the vibration amplitude will be higher, right? So a simple technique is to just take the average of this voltage value and see in the normal working condition what is the voltage value and the faulty condition. Okay, this is for one faulty condition like 0.18 mm, 18 mm cracks on the REB. Okay, for that you have inner layer, outer layer, and rolling element. When these points are on these three layers, you can see what is the average value, right? And they are of course far away from the normal when the machine is in normal working condition, right? In this case, I can just write one line of code and put it on the IoT sensor, right? And then ask it to send the samples to the server only if they exceed, like say for example 20 millivolts. Right? In this case, I'm just trying to stop all the samples unnecessarily from transmitting. Right? I mean, this is a clearly straightforward case where you can do hierarchical inference. It's just taking average locally for a few samples and then classifying it as a normal working condition, and then the rest you just observe. So, did you feel like I'm cheating here? Okay, this is like a straightforward method we can already do, right? Usually sensor sample periodically. Yeah.
Offload to do what?
To know which fault state the machine is in, right? Of course, we need the help of the edge server, and we need the help of the CNN. When how to detect which fault is it, like in the inner layers, outer layers, or the rolling element itself. For that, we need the help of CNN. But whether it is in normal working or is it in fault state, we don't need, because I can just set this threshold here. Okay. So here, to answer the question on which are complex data samples, which are simple data samples, in this case, which are simple data samples. So when the machine is working in the normal state, those are all simple data samples. And the other ones are complex data samples. So that's all. Differentiate. Okay.
So why is the accuracy 100%? This can also lead to some errors.
Yeah. So for this data set, it's 100%. You can just write the code and you can check. Or everything gets classified correctly.
But in principle,
yeah, in principle, because the data set is already refined, right? So they take all number calculators and so.
no, but I think also if you divide the data, so I think the normal then taken to be one and testing. Of course, it's not 100%. I don't think it's. I think if you divide
It's not 100% accuracy for the CNN. It's 100% accuracy for differentiating.
No, but even that, like suppose the nominal is 16, right, and plus minus say 2 millivolts, right? And your best data set, suppose it came out to be 17 only, right? And set 18 was also normal, but you detected it to be error. It's possible, right? Depending on how you divide it.
Just the values in the data set I have, I didn't find any. Right? Whenever I'm taking 64 samples and average, usually, not usually, all the faulty conditions are greater than 20 million.
This is for the vibrations. Like all these voltages are according to the vibrations.
Yeah.
Sensor.
So you get based on the vibration, you get a voltage reading for the sensor.
So it's like machinery, like this heavy machinery is there and some like somewhere is hammering somewhere else. That vibration it can take off. And even though motor is not actually working, it's working normal. But the vibration sensor can take it as a reading, right? Can that happen?
So this is only the data that I am working on. The actual readings were taken in a lab. So yeah, and not that knowledge how they cancel all this. Okay. So let's move on to the more interesting application that I want to talk in more time here. Is how do we do HI for image classification, which is the most sort of single application I would say for last 20 or 30 years. So this is the work done with Vishnu Murthy and James Roth from ATH. So what is the main issue with thinking of doing this hierarchically is the DNNs that are used for image classification today, they are all black boxes. And whenever they are giving some inference, we don't know whether it is correct inference or wrong inference and why is it giving this way for this image and not the other way. So in this case, again, let's go back to the first requirement. I was telling what is the main what is the main ingredient here? We need at least a local algorithm running on the image sensor, right? And that should have less memory requirement and less computational complexity as well. Okay. Fortunately, there is a big research community, tinyML research community, working on this machine learning model, which can be embedded on small devices and still give reasonable accuracy, 40, 50, and 60% accuracy on big image data sets like ImageNet. Okay, so we will just directly borrow one of these small size DNNs, which is a mobile net. And if you see for mobile net, this alpha is the hyperparameter. So based on that, you increase or decrease the size of this mobile net. With alpha equals 0.25 and it is quantized with 8 bits. That neural net has model size 0.5 MB, which can be even you can fit it on even a microcontroller, right? And its accuracy, of course, are very low. It's 39%.
Just a question. Like instead of tinyML, can you now do something simpler, single process? This is very
Yes, definitely. I would like to see that.
If just like so poor accuracy, and if I toss a coin, I'll
Right. I mean, I completely agree with you. My view is that you can have any algorithm on the sensor. It can be any pixel or classical statistical algorithm. But for data sets like ImageNet, I don't know. I have to do more.
Oh, it's fine. I'm just curious. This 40%
Yes.
is very bad.
Right. It is. And then the state-of-the-art algorithm, the POCA gives 91% accuracy and the model parameters size greater than 30 GB. So we try to employ mobile net on the local sensor. And the next requirement is the image sensor need to differentiate correct inference from incorrect inference output by this mobile net. Right, this is again the catch-22 situation I was talking about. Whenever the mobile net gives me an inference, whether it's a cat or a dog, how do I know the ground truth? Right, I don't know. I can never know. Right. So let me just assume for this talk that there is a human who says in the end when the image sensor tells a cat or a dog, okay, a human user views the feedback. Okay, for this talk. We also consider the case we don't have the feedback, but we won't have time to discuss that. For now, in this talk, we'll assume that there will be a feedback in the end. Once the image sensor views the output, after taking output from DNN, it decides whether to accept it or not, and then it output, then immediately it gets a feedback. And the second ingredient is the sensor. I mean, this image sensor, whenever it doesn't want to accept the instance, it can offload to an edge server, which has, say, a big neural network like Poca, which gives with 91% accuracy. And then the second assumption I'm making is, whenever I send to an edge server, I get the correct input. Okay, just for simplicity. Okay, but if you're just assuming that it doesn't give correct input, it only gives input 91% accuracy, we're trying to learn as best as possible. Okay, it doesn't change much. So whenever sensor is sending the image to the edge server, it will get an inference from the edge server, which is the ground truth. Okay, I'm assuming that, and then it can learn from that. It can learn whether the local algorithm, the mobile net, is giving correctly or wrongly an inference. Okay, agreed? So these two are the main things, and we need some more effort here. We need to also understand the mobile net output. I mean, this is the basic understanding of mobile net output. Whenever you give an input, the mobile net uses the probability mass function on the classes, okay, to which this image belongs. Okay, and then in that probability mass function, whichever is the maximum probability, you actually output that as the true label. Okay, and the top one accuracy here, or the average accuracy of the models you always look at, is computed based on this true label and the ground truth. Okay, whether it matches or not, or how many images it matches, you get this accuracy, top one accuracy. Right now, I say that let's take that p value. So here p is again the maximum probability in that probability mass function you get, and then I will say this is actually the confidence of the mobile net. Can I say that or not? Right? That is the confidence with which we are saying, okay, this image belongs, and it is, when it says it is dog, with 80% it is dog. Okay, this is the true label I want, because the 20% is cat, right? So that is the confidence. Now, if I use that confidence P of this DNN output, and then I plot how many number of samples are correctly, actually the true label matches with the ground truth, how many number of images it doesn't match, right? In the blue is the one that matches, in the brown that doesn't match, in the thick one is the overlap between these two. Okay, so when we say the mobile, I mean, deep neural networks are indeed black boxes. So because of this, right, there is no clear separation. We don't know, even if it says with high probability 0.9, we get wrong classifications, right? The thick brown, right? So now here, what I call complex data samples are these brown ones, because this is where mobile net is making mistakes, and only these ones I want to offload, right? The blue ones I don't want to upload. I don't want to waste energy. I don't want to waste any additional processing power, additional bandwidth, and things like that. Right? Ideally, that's what I want. So if I know this is exactly the way mobile net views output for this particular image database, then I want to just put all the blue ones locally, do the inference, accept it, and all the brown images belonging to this brown histogram, let's solve. This is the ideal scenario I want. Okay, but of course we don't know that. Then what is the best we can do? Can we set a threshold? Right, because I am saying P is my confidence. Right, if my confidence is high, I accept the inference. If not, I just offload it and get the inference from the bigger from the edge server. Agreed? Okay.
So here, how is P confidence? Because let's say the P value is 0.3. That is the largest value of P, right? The PMF.
Right.
Now let's say it's 0.3 and there is another P which is 0.29.
Right.
So in that sense, both are close together, right?
Right, exactly.
So you are not sure which of these two classes it should belong.
Right. But when you are classifying, you have to make a decision, right? You need a decision rule. Then usually when if it is top one accuracy, then you always take the label with maximum probability as two label, and then you compute the top one accuracy. This is what you see in the number, right? So, I mean, this is not ideal, but this is how we classify it. I mean, you can also use other metrics like take Pmax and take difference between Pmax and the second highest value, multiply it and see whether this is the confidence interval. I mean, this is a good point actually. We are now doing. We also did use that as a confidence. The metric where you multiply Pmax and the result between Pmax and the next second highest value. And you get even a slightly better results. But for this talk, I'm just saying Pmax is my confidence metric. The analysis will still be the same for both. Now the question is how to choose such threshold. So immediately you can I mean these are trained models I'm talking about. Once you when you're trying itself, you can find this threshold, right? But the issue is your input arrivals of the images can be from different distributions from different databases, right? So this threshold that you compute just when you're doing training of the model might not be ideal, right? So we need some kind of learning to find the threshold where we can actually try to maximize the offloading complex data samples and retaining simple data samples. Okay, so that's so next I think 15 minutes or so we'll focus on that problem, which is going to be a very interesting learning problem. Okay, any questions? Yeah.
If you for even for complex images, you are running the inference and then deciding whether to upload or not.
Yeah, that's the price you pay. You have to first run through.
Yeah, so but then what about the energy consumption versus running all of the samples complex plus simple on the edge device versus just uploading all of the samples to?
Then you get 39%. Just if
Yeah, because then you are running the inference twice. You are running it on device also, edge device as well as on the server. Just try, and you are also aware that the complex images make up more than 50% of the data that you will get.
Right. So that is the price we pay. So without doing anything locally, you cannot infer anything, right? It's again you need some information locally to make a decision, and hoping that is, as I said, the very first requirement is that whatever local algorithm you're using, the computation energy of that should be less than the transmission energy. Otherwise, all this I mean, I don't care, right? Otherwise, I just offload. So you need a small computation energy and you need as small algorithm as you can on the IoT sensor. And this is all still in words only, right? If you go to actual device and do all these things, it can be really hard. But this is still a proposal phase, I would say, right? I mean, I get your question. I don't have an answer, okay? But we have to pay that.
I mean, the question is, what would you use? You have to decide. One thing could be it's just probabilistic. Decide every sample. Decide I'm going to upload it or not going to upload it. I don't know if that will be important. It give you some energy saving, but
yeah, we don't know what is in that sample.
Using some more energy and
I mean, if you don't have any information, what are you going to base? You just can do random, right? I decide with certain probability, I'm not going to do it.
And then you can have any adversary designing some kind of input data that you move them.
No, I think it's okay. It does not affect adversary. Even stochastic model, I mean, you will end up paying the price for transmission, right? Yes.
So yeah, let's I think that we are passing images through a mobile net first, and then we have a meta learning algorithm, HIL, that takes the T is the round, okay, or the T image. We are having the sequence of images. You take the PT as input, and this HIL decides whether to accept that inference, in which case it use the output inference. Once you get an output, you present an output and you will give a log feedback that it is correct or not. Or if you may decide to offload, in which case you get a correct inference from the edge level. Okay. And as I said, the offloading rule is if P is below a threshold that you set, which the algorithm will set, and it learns that threshold, you offload, or else you classify and output the input. The aim is to learn this best threshold that minimizes the number of images. And there are two scenarios. One is local feedback and no local feedback. As I'm saying, I am considering local feedback for this talk. So local feedback also we can deal with it, but it's maybe I'll try to use that one. So images arrive dynamically and we index each image using P. I use this beta, a cost for offloading an image. Okay. And a cost for accepting local inference for image T is YT. And YT depends on the DNN itself in the first place, okay, whether it gives the mobile net, right, wrong inference or correct inference, and of course how you the sequence of images coming. So if YT is 0, we assign YT equals 0 if the local inference is correct, else we assign YT equals 1. Now at time T, given this threshold theta T, the cost incurred or the loss will be YT or beta, and based on whether your threshold is smaller than PT, okay, you accept it and you get YT as the cost. If it is if your threshold is greater than PT, you go and get beta as your cost. Now the total cost for any images is just summing the losses. And here is the problem statement. There exists a fixed threshold for which you minimize this total loss. Okay, and with respect to that particular threshold, we want to minimize the repeat. And the standard setup is you want an algorithm which has a sublinear. Any questions so far? This is the standard learning setup. And now,
So, one question.
just to put,
Yeah, sorry. Here, your two costs are somewhat different, right? They are different in nature. Like one is the cost of like computational cost, the cost of like sending the images or communicating the images, right? And one is the
Right.
cost of making a wrong error.
right.
So, and yeah, so in that sense, you're combining costs of two different
Right.
nature into a single cost.
Right. So here the main aim is to minimize the number of data samples which are correctly classified. Okay, to minimize offloading the number of correctly classified images. We are not specifically looking into energy, delay, all those aspects. Actually, that eventually we want to look at. But here, just to show a proof of concept that using this HIL, we can actually minimize the number of samples we want to upload that are correctly classified. So using this structure, we'll show that it can be done. Yes. So this is the problem statement, and then to put this problem into context, it happens to be a predictions with expert advice. If you look at predictions with expert advice problem, there are n experts, okay, telling that this might be the value of, for example, stock market value, and you believe one of the experts and accept the prediction of that, then you get a payoff. Okay, and okay, that whether you get a reward or you get a loss for that expert, and you also know what rewards or losses you get listening to other experts. But that's that's a classical PEA problem, and there are algorithms which achieve root n log capital N by 2. So the root n is the horizon, the number of times you are accepted or you do this experiment. Okay, this expert. Capital N is the number of experts. Okay, and this also happens to be a lower bound. There is no randomized algorithm which can do better than this. Now, in our case, the experts belong to this domain 01. So expert is the theta, right? So which is the theta threshold, okay, based on which you want to offload or not offload. And immediately one can do uniform discretization. This is something that's been done in MAB problem. So you discretize and then assume your loss function is convex or smooth and try to obtain this root n log n kind of bound plus some loss. Okay. But these approaches are not applicable because in our case we have a discrete loss function where if you are offloading you get a different number, and if you are not offloading you have 0 or 1. Okay, so we cannot assume it's continuous. Or if it's not continuous, it's not convex, and so we need a new algorithm that we can I show and for the analysis as well, and more importantly we need low complexity. Okay, because for each decision we need to spend as much less time as possible. So fortunately we were able to find a structure in this problem. What that says is that the loss function happens to be a piecewise constant function in the intervals created by these Pmax values. So remember that we are looking at the Pmax values on the DNN. Okay, if I collect all the Pmax values for all the images, even n images, I can plot that on a 0, 1 interval, and then I can get at most n plus 1 intervals. And the loss function happens to be, the loss function is the sum of losses that you collect in n rounds, happens to be piecewise constant in this interval p1, p2, p3, so on. Okay. So now, if I know all these intervals a priori, I can use the classical algorithms proposed for predictions with expert advice. Okay, there you have n expert, here you have small n plus 1. So this is different from capital N. N is the number of experts. Here you have small n plus 1, and is the horizon also here. Using this n plus 1 experts, you can achieve similar bounds using this lemma, because this lemma says that you have constant value for this function in each interval.
Beta is communication cost here.
Yes. Then
So-
you're uploading.
So it's it can change with time, right? Or it's given.
Yeah, so right now for all images we assume them like they are same size, and then whenever you are uploading, we assign the constant cost. But you're right, we can actually consider a case where you get the channel and then make a decision.
Mm.
But that would be more interesting. That we are yet to do. Any question? Yeah. So once we have this structure, you can instead of doing uniform quantization, that usually in the literature it is done to extend EW, exponential weighted forecasting algorithm. We have to do non-uniform discretization like this, but the catch is we don't know this Pmax value because the images are arriving over time. Okay, so yeah, this is just stating what I just explained. So if the sequence is known a priori, you can just use the exponential weighted forecasting with n plus 1 intervals as experts, and then you can get a regret bound which is put small n ln n plus 1 by 2. Again, I'm repeating small n here is the total number of images. So we already know for predictions with expert advice problem, if you have small n plus 1 experts, this is the lower bound. Okay, so if you know the Pmax values for all images a priori, you can achieve that bound. Okay, the lower bound using exponential weighted forecasting. But then you don't know these values a priori. So this is a challenge. So how then what is the algorithm that we can use, and what are the bounds we can do? without knowing this Pmax value. So here is a straightforward extension of exponential weighted forecasting. So it is exponential weighted forecasting is in discrete domain because we have an expert. So here we have continuous experts. So what it does is you assign for all theta a weight 1, and then whenever an image arrives, you look at the PT value and then choose a threshold theta with this probability density. Okay, so simply normalize weights. Okay. And then you use the offloading rule. Okay, if the threshold is, the PT value is less than the threshold, then you offload. If it is greater, you accept, and then you get this loss. Right? With this loss, you modify using the exponential weighting. You modify each weight for each theta. Okay. But of course, this is computationally complex. You cannot possibly implement it, okay? Because you cannot do for all theta values this update in every decision, right? So, but again, fortunately, because of the lemma since it is a piecewise constant function in each interval, we were able to implement it in such a way, that the complexity is reduced. I'll show you. Yeah. So the regret bound for that HLF algorithm I just showed is √8 ln 1 by lambda mean divided. Sorry, that's a learning rate theta. Sorry, I forgot to mention. For HLF, which is √n ln 1 by lambda mean by 2. Now there is a quite a similar aspect as the bound I was already showing from PEA, which is that here is in case of 1 by lambda mean, you have that capital N is the number of experts. Now what is the 1 by lambda mean here? The lambda mean is the minimum of those intervals, PA. So remember, these are our experts. So if we know these experts a priori, then we would have the best bound. But since we don't know this optimal threshold could sit in any of these intervals. So we are taking the smallest interval, and this is the limitation of the bound we do, because the smallest interval lambda mean, the size of that interval can be anything, right? It depends on the data set itself. So this is the limitation, but yeah, we are trying, but it's not without much success. But this is the bound we have so far.
So,
yeah.
How did you choose ITA? Why did you choose ITA as that?
Yeah. So what happens is when we do the analysis for the regret, we get on the right side the function of beta, which has eta plus 1 by eta kind of function. So in that case, you can choose eta such that this bound gets minimized, and that's how this bound will result in this bound. Of course, yeah. Then since we don't know lambda mean, how do you choose eta? A sensible choice we found is just choose lambda mean equals 1 by n plus 1, which means we need to know the value of n a priori. But then now we are using dynamic eta also, where you don't need the value of n a priori. So, but this is a standard technique in the literature. So for now, we'll show the results by choosing lambda mean equals 1 by n plus 1.
No, mistake.
Right.
1 by n plus 1 sort of resolve. He has an equal space.
Exactly. This is because we have the n value. We tried with this and it is working well, and we are kind of.
But this is optimistic. This is not your worst case would be when your VIs are very small.
Small, right? And that's where the bound is.
I also sort of feel that the bound is fundamental. You cannot improve it. That's the hardness of your problem.
Right. I also believe, but
yeah, you need to prove, but I think it's not easy to do that.
True. Actually, we there are other algorithms that follow.
So what you need to do is find the lower bound. Actually, show that nothing you can do will do.
Yes. So lower bound is there, but lambda mean can be much. Well, lambda mean can be much higher than.
If you find the lower bound, in terms of BIs. I mean, I don't know if that's then you know exactly what's right.
No, but in terms of BI,
I mean, I don't know. Like
a genie can achieve this, right? So this is kind of the law.
no, but that's a bit extra information, right? If you remove that, that's one lower bound, but it's probably not the tightest.
No, this bound is tight, so genie can achieve it.
So genie can achieve it, but that is assuming extra information which you don't have. So if you don't have information, then you need another lower. Right?
Yeah. So that I don't.
So that one will probably tell you that you cannot beat what you have solved.
Yeah.
Because it looks to me the hardness of the property.
Yeah, I'm not sure there. So might be or might not. You might be right.
I mean, what do I know? You're the one who's done this research. But
No,
I feel like it's
I don't know if there is a better bound here. Okay. So coming to the complexity, as I mentioned.
the reason I'm saying that, when you do this UCB kind of stuff, right, and you talk about different arms when you're picking, right, and the difference between the mean of two arms, right, and it is the ones which are the closest, in the end you get stuck. That if they're too close, then you cannot distinguish between these arms. So I think intuitively seems like it's a similar kind of problem here.
Yeah. So that, yes. Yeah, it could be right. Okay, then as I said, the computation complexity of that algorithm, which we use the same principle from lemma 1, and we implement in such a way that the complexity is O of t, where t is the round. Tth image, but tth image we have to go through the computation complexity of O of t. We can still further reduce it by making it a little bit more heuristic by limiting the number of intervals that HL uses.
So one more question, why is it the bound increasing with n?
Yeah, so this is the cumulative regret. If you divide by n, you get what we want is ideally a sublinear regret. Here you get it, but the lambda mean is something still in the air, I would say right now. But as I pointed out, this could be the best.
You told like afterwards you'll be going dynamic, right?
Yeah. So if I don't know small n, so I'm assuming right now I know the small n because I know that I have an image database and I know the number of images. Right? So if you don't know, you can use dynamic eta. Okay, wherein you just use that t for t image, you write eta as a function of t instead of instead of lambda mean, which of course you also don't get rid of. And there is a technique, standard technique. Yeah. Okay, now let's go to the fun part. So we have two data sets. One is ImageNet, image group. These are both subsets of ImageNet, the big data set. So image NETE contains 10 classes and image groups contains 10 classes, all dogs, different breeds. So this is harder data set. We use 4 baselines. Genie, which knows exactly that figure I showed, complex data samples, simple data samples. Okay, and then there is optimal 6 threshold, theta, and then full offload, no offload. So full offload is just offload everything, no offload is just accept the inference of the local DNN, which is in space. So in this figure on the left, I'm showing for dataset ImageNet. On the right, I'm showing the average cost for image groups. Forget about HILN, the light blue curve, and other. If you look at the other curve, let's first focus on no offload. So no offload is you are accepting whatever you are getting from the mobile net, the true label from the mobile net, and you can see that for ImageNet, which is a subset of ImageNet, it has accuracy of approximately 43%. So from the top, okay? From the bottom, the cost exactly represents the number of mistakes it's making. Okay. And then if you're using full offload, right, and then increasing data, right? So when I'm offloading, the cost is simply data, right? So as I'm increasing data, the full offload case increases with data linearly. So the most interesting one here are for us the theta star, which is the optimal threshold data, okay, where which is shown in green, and HILF. Okay, we are comparing with the optimal threshold data that can be achieved, and HILF and it they are very close for all values of data. And the same you can observe in image proof data set when there is no offload. You see the accuracy of mobile net is worse. Here it is 30% from the top. 70% are getting classified wrongly. In this case also you see similar trend. Okay. So the main observation I want to tell is the HLF closely follows the optimal fixed data policy. And let's look at the top one accuracy. Now you may ask me the question, so why are we doing this? Okay, why are we doing this? What is the main aim of just using some beta 0, 1 values? And I was telling previously, we want to offload only complex data samples and retain. And let's see how we are doing in terms of that. So for this is for image NETT database, where Genie will be uploading 2230 images, which means there are in total 3925 images in this database. Genie is offloading only the images for which the mobile net is classifying wrongly. That is 2230, and full offload is simply offloading everything. No offload is just 2230 images are getting misclassified, right? And theta star and HLF is these can be in between, right? So if you are choosing optimal fixed threshold, 302 images are being offloaded, and 970 images which are not offloaded but misclassified. And if you look at HLF, it does similar numbers, right? So 1668 images are offloaded, and whichever not offloaded, among them 883 are misclassified. So what does this tell? So just forget about HLF for now. So what does this tell? If I am just not using the help of the edge server, okay, I know I get a poor accuracy, right? Which is 39% or 40%. If I am using HILF, I am offloading 1668 images which are all wrongly classified, okay, for which I am getting correct classification. 883 images in total I misclassified locally, okay, but whichever locally correctly classified images I am trying to retain as much as possible. And here the accuracy of HLF is 77.4%. So compared to not offloading at all, we are improving the accuracy from 39% to 77.4%. Okay, by retaining which are correctly classified and only offload them by maximizing the number of images you are correctly classifying locally. Okay. So this is the main gist of hierarchical inference that I want to show. So this is the reason. So we choose beta, and for beta equals 0.7, these are the numbers. But other beta also we get similar numbers, and the choice of beta is something is still abstract right now. But as you asked, it could be more system oriented parameter, like based on energy, transmission energy, computation energy, which we are very much interested in. Any question?
I think we're above time.
Yeah.
So we'll take it up with that.
Okay, so few questions from online audience. That in a single same image, is there any possibility of having simple data and complex data?
No, we are not classifying simple and complex for a single image. It's more like, at least in here, the approach we use, we are trying to look at Tmax and then classifying it as simple or complex based on the confidence.
Yeah, and is there any chance of getting altogether different inference when the local infer data is sent to online server? Have you discussed, right? Yeah, is there any chance of getting altogether different inference when the local inferred data is sent to online server?
It is right. This is what, so the online server, the remote server, which hosts a big data big DNN, does you correct inference in more most images than the local mobile.
That's all. If anyone have any questions, you can.
Use this.
Thank you for the topic, and the video and the slides will be updated in our web. Thank you, everyone.
Thank you everyone for your time.